This one, on this one, we're starting the third part of the Weather Nerd 101 playlist. Still in the topic of severe weather, and we're going to be talking today about capping inversions and how they can either inhibit or enhance severe thunderstorm development. We're also going to go ahead and take a look at radar images of tornadoes, and also getting a little bit into the bow echo stuff. I think I'll get a little bit more intricate with the damaging wind and bow echoes and line segments in a different video, just to try not to make this too long. I know the last one was really long. Also, before I get started, I appreciate the support that last video got too. Surprised given how long it was, but seems like you guys kind of liked it. If so, I appreciate it. That one took a little while to make. Even beyond just what you saw, there was a lot that you didn't see that I had to cut out. But yeah, anyway, we're just going to go ahead and get right into this. So we're going to start out with the capping inversion, or the cap in the atmosphere. So this is a diagram of what the cap is, and basically what this entails is we have our warm temperatures at the surface right here, right? But the further up you get into the atmosphere, the temperatures start to decrease. That's how things will normally work. What a capping inversion is just that, an inversion where we have an area of warm air aloft that comes in and basically stops that warm air from rising into the colder air of the atmosphere. So this little area becomes what we call the cap, or capping inversion. And what this will end up doing, if it's strong enough, it'll stop that warm air from rising, and this is what you would need in order for thunderstorms to form. So basically this cap becomes a deterrent for thunderstorms. This cap, however, can be broken. So scroll down, and here's what happens when we have a capping inversion with surface temperatures that are increasing with height. Sun heats the surface layer, so it becomes warmer than the capping layer, and normally this is how it would hold. But then here comes a cold front or a disturbance that can end up eroding that cap over time. So in most cases, if the cap holds in this situation, I think you lean a little bit more towards the damaging wind event versus a tornadic event, because you want more discrete cells to form. And this is what the cap is very ideal in causing if one breaks early enough. The timing of when the cap breaks is always going to be a key factor in severe weather genesis. So the two ways a cap breaks the easiest is, of course, through a cold front or cold air flowing through. Then the other way is an upper level disturbance, like an area of low pressure ends up lifting the cap layer. The capping layer, whenever it's lifted like this, that's when I'm a little bit more concerned with the potential for severe development, especially development of supercells. So we have to be extra watchful of that. So basically, with no cap, this doesn't happen. And I'm sorry that that's such a small picture. Here's a little bit of a better view of it. But simply put, this storm without a cap would probably be up to this height, maybe, if it formed at all. But once that cap breaks, this happens very quickly, and this storm is probably reaching about 45 to 50,000 feet. And one thing to note here is the stronger the storm, usually it's going to be the stronger storm's usually going to be a lot taller, simply put. So the taller the storm, the stronger the storm. That's what I was trying to say there. But that's pretty much all we have for the cap here. Now we're going to go to applying some of this knowledge in a more practical application. So what I mean by that is, some people I understand that may watch these videos aren't really into the whole intricacies of weather, and that's okay if you aren't. I don't hate you for it, but what you want to understand most is the radar, and we're going to show what happens when that cap breaks, what it can look like on radar, and we're also going to start getting into reading certain weather hazards on radar. So let's go ahead and take a look at this here. This is actually sampled from the November 4th event that hit over towards the Red River Valley. So I set this into a loop here, and you can kind of see this little boundary form once the cap breaks. Then right around here, these storms to the south start firing. And then ultimately, it's these storms here that we ended up watching become supercells, eventually becoming tornadic, and then of course we saw the results of the November 4th outbreak. It was all over the news. So simply put, that's the situation there. So now let's actually go ahead and take a look at what these supercells ended up looking like when they started producing tornadoes. So this is another this is sampled from another storm on November 4th. And this is an isolated supercell. This is more ideal conditions for tornadic development here. These other storms could also produce tornadoes, and some of them would later, but these discrete cells are always the ones you want to look out for. Now there are some very distinct characteristics to look at. You have, of course, this little hook echo region right over here. Whenever you see this little tail of the storm start to curve, like come down like this and start to curve inward on itself, that means the storm is rotating, has inflow or warm air feeding into it, and then cold air wrapping around the backside, so it has a pretty significant amount of rotation. Usually when you see this, almost always you would get a tornado warning right after. This is one of the classic textbook signs in tornadic development here. So one other way you can pick up on a tornado on radar is looking at wind velocity data here. And this is a similar storm. I think this is actually the same storm that I was looking at on here. This was heading towards Gilmer. So I zoomed in, took a closer look, and went to a wind velocity data sample. Alright, so the way you read this one is we have these two colors here. We have green and red. These two colors represent winds going towards and away from the radar. Green is indicating winds going towards the radar. Red is winds going away from the radar. So if you think about it, when these two wind directions are coming in close together, that's almost a telltale sign. That's almost a dead giveaway that this storm is rotating. When these red and green couplet form right here, you can kind of see it here. It's one going towards the radar. Here's one going away from the radar. Instantly, you start to think, okay, this is where our tornado could form right here. It's pretty simple. There's another way to pick up on a tornado, and this is actually a little bit more of a depressing one, if you ask me, because when you see this model, this means that debris is on the ground, is being lifted up, it is being taken off the ground, lifted into the air. This tornado is doing damage, basically. And this is called the correlation coefficient. What this does here is this actually looks at meteorological objects through the air, basically raindrops. So if you get regular raindrops, you're going to get this color right here. You're going to get a lot of pinks. You're going to get a lot more the red color. When you start getting into non-meteorological objects, the coefficient will start to drop, actually, which will make this color right here. And when you start to see a shape about like this or bigger, or almost in a circle, like a circular shape, this is almost indicative of a tornado, unfortunately. So when you see your local news station or any of your favorite weather YouTubers or the weather channels show this usually is a guarantee that a tornado is on the ground, unfortunately, and it's doing damage actively at that time. So if you see this and it's heading towards your area, this is the real thing. This is not some false tornado warning. You need to take action, and you need to take action now to protect yourself and your families and maybe your property. But if you usually see this, and like say you were close to New Boston, for example, time's running out. You need to take shelter immediately. So let's get a little bit more intricate with tornadic activity here, with the radar activity here. This is looking more back towards the traditional radar or resolution radar. Like I said, we've already talked about the hook echo. We've already talked about the vortex couplet or velocity couplet. Now, here's one telltale sign of tornadic activity as well, and that is the V notch or the flying eagle. That's usually towards the front flank of the storm here. Usually, you'll have this notch here, but this usually will indicate like the strongest of supercells. The updraft of the storm ends up becoming so strong and so tall, the upper level winds end up being forced around two different parts of the storm, and this spreads the precipitation outward. If you watched my last video, we talked about how speed shear ends up forcing away the rain and precipitation away from the updraft, and this is an indicator of just how strong that speed shear is. And then, of course, we can always look at the high resolution radar and get a look at what's called the debris ball. Now, you can look at it on a correlation coefficient. It would be relatively the same thing, but it's more alarming actually whenever you see the debris ball return here on this type of radar, because that means that debris is being lofted very high into the atmosphere. I mean, in either situation, it's not good, but whenever you see it on here, especially as well defined as what you see in this picture, right here in the middle, that means odds are it's a pretty strong tornado, or it's going through a densely populated area here. So we'll backtrack here, and we'll actually take a look at a couple of other areas where we could look at potential tornadic activity here. And this one's a little bit more advanced. This one's called the bounded weak echo region, or BWER for short, or the elephant trunk. This is when we get what's most likely our most dangerous type of tornado. Storm chasers are very familiar with this. It's a rain-wrapped tornado. So we can't get rotation. We can't get a precipitation to fall right around the or right in the rotating updraft area. Otherwise, the storm would fall apart. But the weak echo region allows for the rain to fall around the outside of the storm, and usually you don't look at this through a traditional radar image. You have to almost have a 3D radar and look at it through a vertical cross section. And here's several good examples of that. Sometimes this will also be reflected through a look on the traditional radar as a donut hole. So that's something to look out for as well. There's plenty of ways to look at things on radar, these supercells on radar, and get an idea of tornadoes, but these are the basics. Whenever you start to see these signs and you see these heading towards your area, now, like I said, now would be as good a time as any to take shelter. Because if you wait too long, these storms can evolve and become much more dangerous and maybe a little less survivable. Hate to sound morbid, but the easiest way to get hurt or worse in a tornado is by not being prepared. So let this be an informative lesson, so to speak, on how to prepare for a tornadic event. So there's one other thing that we're going to go over here before we close out this video, and this is it right here. So we talked about the traditional ways you can pick up a tornado on radar. Usually that's going to be associated with discrete supercells, but tornadoes can form in line segments called bow echoes and QLCSs, so to speak. QLCS is a quasi-linear convective system, or a line of storms that has embedded supercells in it, which can produce tornadoes. Now, with the bow echo, it's a little bit different, and it's a little bit more difficult to detect these tornadoes because they happen extremely fast. But we're going to quickly go over how that forms, and we'll go from there. We'll be more in depth with the bow echoes in a video in the near future. I'm putting emphasis on this because I'm making this video during the fall, and that's when this will be released. And fall and springs are the times where we have the most active weather, and there's the greatest chance for a collision of warm and cold air, leading to severe thunderstorm development. So, back to the bow echo here. We look for these little comma heads on a bow echo here. Usually they'll be towards the top of the storm, of the storm system here. Excuse me. And right around that little bow apex where it kind of notches out like that. Sometimes you can get some rotation to develop here, and you can get a quick spin up tornado. More often than not, these tornadoes are not strong, but they are still dangerous nonetheless. And you can't bank on every bow echo tornado to be weak, because there have been a few cases where they have been strong. We've had EF3s and EF4s even. But basically how this works, here's our weak echo. Here's our weak, can't speak right now. Here's our WEC. Here's our main area of interest. And of course, this is where a tornado forms. Here's our radar couplet right here. Red's indicating when it's going away from the radar, and right up against it, there's a little area where those greens and reds touch together, indicating rotation. And here's a better look at what's going on here. Right to the north, there's our stationary boundary. Here's our cold front, and then out ahead of it, there's warm air feeding into the storm right here. This area right here is what you call an inflow notch. That inflow notch feeds the warm air. You get the cold air coming around that, and then basically it's almost the same thing as looking at this velocity couplet here. In this case, this wind going towards the radar here would almost be warm air, and this right here, this red area would be cold air. Those two would mix together right here, and then you get your thunderstorm and your tornado. But like I said, usually with this kind of setup, these tornadoes form quick and they don't last long, but they can still do plenty of damage. So again, use what you've learned here in this video if you made it all the way to the end, especially on in regards to potential severe events in your area, because it can easily happen. It's happened everywhere in the U.S. in the past, and if the conditions are right, it will happen again. But that's enough for this video. Been rambling plenty. If you're really into this playlist, definitely drop a like. Let me know in the comments what your thoughts are. Of course, subscribe if you haven't already, and share the video to anyone else that may be interested in becoming a weather nerd or already is. But yeah, this has been Tire Metalhead Weatherman. I'll see you guys in the next video. You guys enjoy your day. Less than 20 minutes.